I'm going to derive for you the Maclaurin series. We start with a power series for a function. So assume that a function f of x is defined by a power series c sub 0 plus c1x plus c2x squared plus c3x cubed plus c4x to the fourth, and this goes on indefinitely. So we can write it as the series n goes from 0 to infinity, c sub n x to the nth power, where c sub n are the coefficients of x powers. We're going to assume that the function f of x has n derivatives. We'll start by taking derivatives. The derivative f prime of x is the constant disappears, derivative of a constant is 0, and we get derivative of c1x is c1 plus derivative of c2x squared is 2c2x to the 1. The derivative of c3x cubed is 3c3x squared. Derivative of this is 4c4x cubed, and this will go on indefinitely. Second derivative, the derivative of the constant disappears, and this, of course, is 2 times 1 c2, x to the 0 is just 1, and then we have 3 times 2 c3, x to the 1, and then 4 times 3 c4, x to the second, and this also will go on indefinitely. Second derivative, I was multiplying these two, these two, these two. We're now going to take the third derivative. The third derivative of x, the constant term becomes 0. Then we get 3, 2, 1, c sub 3, x to the 0. Well, that's just 1. And then this one is 4, 3, 2, c sub 4, x to the 1. And I'm going to write another term. The next term would be 5, 4, 3, c sub 5, x to the second. And these would go on indefinitely. The fourth derivative, again, the constant term disappears, and this becomes 4, 3, 2, 1, c4, x to the 0 is 1, and this is 5, 4, 3, 2, c5, x to the 1, and it goes on indefinitely. One thing we'll notice here, I have 2 times 1. I can think of that as 2 factorial. 3, 2, 1 is 3 factorial. 4, 3, 2, 1 is 4 factorial. What we're going to do now is we are going to let x equal 0. And in doing that, we're going to find a way of replacing all these constant terms that are in front of the x to the power. Letting x be 0, f of 0, you can see the x's will all become 0, and I'm left with c sub 0. Doing the same with the first derivative, f prime of 0, the x's all become 0, and I'm left with c1. Letting the second derivative, letting x be 0, I have the second derivative. The x's all become 0, and I'm left with 2 factorial c sub 2. Letting 0 for x in the third one gives me the third derivative at 0 is 3 factorial c sub 3, because all these x's become 0. Looking at this pattern, I can see that if I looked at the nth derivative at 0, it would be n factorial c sub n. We are going to now use this expression to solve for all the coefficients. So c sub 0 is f of 0. We can see that c sub 1 is first derivative at 0. Looking at this over here, we can see that if we want c sub 2, we're going to have to divide by 2 factorial. Working that out, we get c sub 2 is the second derivative at 0 over 2 factorial. And working this, we can see c sub 3 will be the third derivative at 0 over 3 factorial. So in fact, using our generalization, we get that the nth constant c sub n is the nth derivative of 0 over n factorial. But when we started, f of x was written as the series n goes from 0 to infinity, c sub n x to the n. We are now going to replace the c sub n with this expression in terms of derivatives of the function. That becomes n goes from 0 to infinity, c sub n, which we replace with the nth derivative of 0 over n factorial times x to the n. And this is known as the Maclaurin series representation. And it's the Maclaurin series representation of the function. What we have done is we have created a new way of writing that function, and it's an infinite series. We'll go on to the next page. We now can write the function f of x as, using this, it's the 0th derivative, which means it's the function f of 0 over 0 factorial x to the 0. Letting n be 1, it's the first derivative of 0 over 1 factorial x to the 1. Letting n be 2, it's the second derivative of 0 over 2 factorial x squared. And then the third derivative of 0 over 3 factorial x cubed. And we will continue on infinitum. This is known as the Maclaurin series expansion. As an example, you guys, we are going to create the Maclaurin series expansion for the function f of x is e to the x. What we're going to do is we are going to set up, first we're going to get the derivatives of the function. That will be our first step. That's our first step. Then our second step is we will set x equal to 0. I like to do the derivative, and I take quite a few. So I go f of x is e to the x. Then, of course, the derivative is still e to the x. The second derivative is e to the x. And in general, the nth derivative is e to the x. That's our first step. Our next step is we're going to now, after we have the derivatives, in this case it was easy. In some cases you have to do 3, 4, or 5 of them to get a pattern. But now we're going to set x equal to 0. So we get f of 0, which is e to the 0 is 1. The derivative at 0 is e to the 0 is 1. The second derivative of 0, e to the 0 is 1. And in fact, the nth derivative at 0 is also 1. We're now going to be able to take this second column and substitute into the formula for the expansion. I like to write the expansion, the formula as f of x is the series n goes from 0 to infinity, the nth derivative of 0 over n factorial x to the n. Looking at this, we see that the nth derivative at 0 is just 1. So we are going to be able to substitute that in the sigma notation. So this becomes the series n goes from 0 to infinity. Substituting 1, we get 1 over n factorial x to the n, which I just write as x to the n over n factorial. This is the Maclaurin series for the function e to the x. I'm now going to write out those terms. So what I know is that my function e to the x is this series from 0 to infinity, x to the n over n factorial, and I then proceed to write out a few terms. X to the 0 is 1 over 0 factorial. Then we have x to the 1, x over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial, on and on. And this is the Maclaurin series for the function e to the x.